Good evening. Myself, P. Ramesh Babu, Assistant Professor, Department of CSC. For this session, I am going to be explain about subject computer system and architecture. In that computer system architecture, the topic is digital logic circuits. In the digital logic circuit, these are the topics we are going to be covered: digital computers, logic gates, and Boolean algebra. So what do you mean by digital computer? A digital computer is an electronic device capable of holding large amount of data and carrying out mathematical computations and groups of the logical process at high speed. So we have the different types of the computers is there, personal computers. So whatever at our home we are using the PCs, desktops, those are called as a personal computers, and notebook computers. Second one is the notebook computer, workstations, and enterprise system and supercomputers. So this is the block diagram of the digital computer. The functional units of the digital computers are input, output, memory, and arithmetic logic unit and control unit. So here central processing is the heart of the computer, CPU, and input device, it take the input from the user. So as usual, input devices are the keyboard, mouse, monitor, joystick. Sorry, inputs are uh, keyboard, mouse, joystick, and output devices are the monitor and printer. And in the central processing unit, so then arithmetic logic unit is there, ALU, and control unit. So ALU stands for the arithmetic logic unit, CU stands for the control unit. So the ALU performs the arithmetic operations like addition, subtraction, multiplication, division, and modulo division operators. Okay, and so coming to the random access memory, RAM. So again, memory is divided into two types. One is the primary memory and secondary memory. So coming to the primary memory, so it is divided into two types: random access memory, read-only memory. Okay, so these are the block diagram of the digital computers. So second topic is the logic gates. So logic gates are the fundamental building blocks in digital electronics. So these are basically 7 main types of the logic gates which are used to perform the various logical operation in digital system. So by combining the different logic gates, complex operations are performed and circuits like flip-flop, counters, and processor are designated. So mainly the logic gates is for the to manipulate the binary information. We are using the logic circuits. So those circuits are also called as a logic gates. So there two types of the logic gates is there. One is basic logic gates, and second one is universal logic gates. So basic logic gates are coming and AND gate, OR gate, and NOT. So let us see one by one AND gate. So AND gate is used to perform the logical manipulation of binary input, logical multiplication of binary input. The output of the output state of the AND gate will be high. So if the both input are the high, else the output state will be low if any one of the input is low. So an AND gate is used to perform logical manipulation of binary input. So the diagram is represented as A. This is the A input and B input, then output is the X. The Boolean expression or Boolean function is written as X equal to AB. X equal to AB. So the truth table is we are passing the two inputs A and B. So then 0 0, the output is 1, 0 1, output is 0, and 1 0, output is 0, 1 1, output is 1. OR gate. OR gate is mostly used digital logic circuits. The output state of OR gate will be high. So if any of the input state is high, so else the output will be 0. Then the symbolic representation as a OR gate is, this is a symbolic representation, and algebraic function equal to x equal to a plus b. So this is a truth table. So then a b x equal to a plus b, 0 plus 0 equal to 1, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1. So OR gate. NOT gate. In digital electronics, the NOT gate is one of the basic block of the basic logic gate, having only single input and a single output. So it is also known as an inverter or complement. Inverter or inverting the buffer. So when the input signal is the low, the output signal is the high. We are passing the value, input is a 0, then output is will become 1. So we are passing the input is a 1, then output is 0. This is called as a inverter or NOT gate. Now, so NAND gate. So NAND gate is another type of universal logic gates. So NAND gate is a combination of NOT and AND gates. So it's a combination of two basic logic gates, AND gate and NOT gate. So connected in the series, it takes the two or more inputs and gives the only one output. The Boolean expression can be written as a x equal to a multiplication b complement. So this is the this is the diagrammatic symbolic representation of NAND gate, and this is the truth table for NAND gate. Truth table. A. So then x equal, that is a equal to 0, b equal to 0, then x equal to a into b complement, then 0 into 0, then 0 complement equal to 1. So this is the 1. So likewise, these are the truth values. NOR gate. So NOR gate, which is equal to OR gate followed by the NOT gate. The NOR gate gives the low output if any of the inputs are high. The NOR gate is represented by the OR gate with small circle on the output. So this circle is represented as a NOR gate. So the NOR gate, and the Boolean expression is represented as a x equal to a plus b complement. So let us see, a equal to, if a equal to 0, b equal to 0, then x equal to a plus 0 plus 0 complement, then 0 complement equal to 1. If a equal to 0, b equal to 1, then x equal to 0 plus 1 complement. So 1 complement is nothing but the 0. So likewise, these are the values. Exclusive OR gate. The exclusive OR gate is a circuit which will give a high output if one of its input is high but not both of them. The XOR operation is represented by encircle plus sign. So XOR operation is represented by encircle plus. The Boolean algebraic function x equal to a b or x equal to a complement b plus ab complement. Now see the truth table for exclusive OR. A equal to 0, b equal to 0, x equal to a complement b plus ab complement. So a complement, a value is 0, then complement equal to 1, 1 into 0 plus 0, this is the complement value is the 1, so 1 plus 1, 0 plus 0 equal to 0. Then same manner, a equal to 1, 0, b equal to 1, then x value equal to a dash 1 into, so b value is 1 plus, and a value is 0 into 1, 1 plus 0 equal to 1. So this is a exclusive OR gate. And second one, next one, last one is the exclusive NOR gate is a circuit that does not the inverse operation to the XOR gate. It will give a low output if one of its inputs is high, but not both of them. The small circle is represented as a inversion. This circle is represented as a inversion. So whenever both the inputs A and B is having same identical values, the output will be the high. And so in this section, in this case also, A value equal to 1, B value equal to 1, then it is the 1. The algebraic function is represented as A, x equal to A XOR operation B complement, or x equal to A complement B plus AB. See the example, if A equal to 0, B equal to 0, then x equal to A complement 1 into B complement is the 1 plus 0 into 0, then 1 plus 0 equal to 1. First take the second case, A equal to 0, B equal to 1, then x equal to A complement 1 complement, B complement is 0 plus 1 into 0, 0 plus 0 and 0. So this is the exclusive NOR or equivalent. Then so this is another name is equivalent gate. Exclusive NOR gate is treated as a equivalence gate. So next topic is the Boolean algebra. Boolean algebra can be considered as a algebra that deals with the binary variables and logic operations. Boolean algebra variables are designated by the letters such as capital A, B, X and Y. The basic operations performed AND operation, OR operation and complement. The Boolean algebraic function are mostly expressed with the binary variables, logic operation symbols, parenthesis and equal sign. For a given value of variables, the Boolean function can be either 1 or 0. So consider the example f equal to x plus y dash z, y complement z. So the logic diagram for the Boolean function f equal to x plus y complement z can be represented as. So let us see here we can use y complement b for y complement b z. So we can use the AND gate, and for these two operations we can use OR gate, and for this we can use inverter or complement inverter. So let us see draw the diagram. So I'm passing the y value here, so then it will coming to the y complement and z. So both are the inputs of the AND gate, then getting the AND output. So this is the output of AND gate will the input of the OR gate. So x equal to x is the one input, and the combination of this output will be the input of this OR gate, and we're getting the f value f equal to x plus y complement and z. So let us see the truth table for f equal to x plus y complement z. So here the variables f equal to x plus y complement z. Let us take let x equal to 0, y equal to 0 and z equal to 0. Then f value equal to x plus y complement z. So x equal to 0 plus y complement is 0 is complement is 1, 1 into 0, then 0. x equal to this case 1, y equal to 0, z equal to 0. Then so f equal to x plus y dash y complement z, then x equal to 1 plus y value equal to 1. This is the y equal to 0, y complement equal to 1 and 0. Then 1 plus 0. So the value will become 1. In the last case, see the last case, x value equal to 1, y value equal to 1, z value equal to 1, f equal to x plus y complement z, x value equal to 1, y complement is 0 and 1, 1 plus 0 equal to 1. So this is the Boolean algebra, and these are the references books: Computer System Architecture, Morris-Mano, and third edition. So Computer Architecture and the Organization, an Integrated Approach, and Computer Organization and Architecture. So this is the William Stalling 6th edition. Thank you.